So we're happy to have Shruti Paranjape from the University of California, Davis, who's going to tell us about loops and a loop expansion.
Okay, so thanks so much to the organizers for the opportunity to speak and tell you about loops and a loop expansion, which is based on work that I did with Yara and two of his students, Taro Brown, who I think just left to catch his flight, and Umut, who's in the back row over there. Yeah. Okay, so. Okay, so loops and a loop expansion. I'm going to try and break down the introduction of this into three parts. Why we are doing this expansion, what is the quantity that we're actually expanding, and then how we are going about actually calculating terms in this expansion. One thing I will not tell you because it doesn't exist is what is the parameter that we're expanding in. And it'll become clear why I'm not going to tell you what that is in a second. Okay, so for anyone slightly unfamiliar with QFT, normally what one does when one calculates the scattering amplitude is you think about this perturbatively in the interaction strength, right? So you say that first order in perturbation theory is tree level, and then you add one loop, two loop, this is a three loop, four loop, etc., etc., etc. So this is a weak coupling expansion, and it's something that's perturbative around G, which is what I'm going to call the coupling, G being small. Now, in principle, you can keep doing this, right? And the hope is that in order to get something at strong coupling, you'd have to resum all of these contributions, and that'll give you something that is now valid outside just G very close to 1. Sorry, 0. Okay, so this is something that people have considered doing in the past. But I will say, so okay, there are lots of these contributions. And in order to resum, you have to choose some subset of these, right? Otherwise, you'd be solving the entire theory, which is not being done. So you sort of, in an ad hoc way, choose some subset of diagrams, and then you do the resummation of that subset. Good. So one example of this was done by Broadhurst and Davidichev. And what they did is they resummed all contributions of this type, right? So this is clearly a very non-generic loop diagram. You've chosen a particular type, but it's a type that you can calculate no matter how many rungs to this ladder there are, right? So they did this calculation and they resummed everything, and they looked at what happened when G was taken large. And for large G, they found that the contribution was order e to the minus G, and G is like very large, right? So this is exponentially suppressed once I do this resummation. In short, I chose a measure 0 set of diagrams, and it gave me something exponentially suppressed. So I shouldn't be surprised, right?
Sorry.
Yeah.
So they did this resummation some particular kinematic
This was in
point.
phi cubed.
Yeah, but it's not like they did. Still, it's a complicated function, so they do probably some point interface space around which they could evaluate linear asymptotics. That's what they sum.
I think in this case they did an honest loop calculation.
Yeah, but they resummed asymptotics at some particular kinematic point, and I was just wondering what is that kinematic.
Well, I mean, this has both. So this is not like some iconal approximation or something. This has S and it has phi, which is the entire contents of the kinematics at full point, I think. Yeah. So another example of such a resummation was done in this more recent paper by Nima, Johannes, Henn, and Yara. And this was for a slightly different quantity, not the 4-point amplitude. But they did a resummation of graphs that looks like this. I know this is meaningless at this point, but stick with me. So they did some resummation. And in their case, it actually did capture the correct large, strong coupling behavior, Okay, so they could actually do a resummation and it gave them something. Now, I'll point out that both of these were ad hoc selections of graphs. There's no reason to believe that this is a good approximation, and there's no reason to believe that the second one is either. It just happened to be that this selection brought them very close to the correct answer. Okay. Good. So the aim of this talk is then going to be, can I go to the next order in the expansion that actually worked? Okay, so can I check whether or not that subset of graphs is genuinely a good approximation to a strong coupling quantity? All right, so that's why we're doing the expansion. I now want to talk about what the exact quantity is. Now, this next section is a little bit physicsy, so I'll try and summarize at the end of this what to take away from it if you're not a physicist. Okay. So it's known from a paper by Born, Dixon, and Smirnov that at 4 and 5 point, all the divergences in n equals 4, they exponentiate in the following way. Okay. So normally for every L loop, once I do the actual, like we spent a lot of time in this conference talking about integrands, but once I do the actual integration, I'm going to get a 1 over epsilon to the 2L divergence. Epsilon goes to 0. So this is a very bad divergence. But n equals 4 is special in that all of these divergences exponentiate in the following way, where this is a 1 loop divergence. So it's actually much milder than you would think it would be. All right. So these are the various terms in this ansatz, often called the BDS ansatz. And in particular, the most singular term is only a 1 over epsilon square, and it's determined by this object that is called the cusp anomalous dimension. Okay. So, right, because this is an exponential, this tells you that the log of the amplitude is probably the thing you should be studying, because that is what's going to tell you this object over here, gamma cusp. And it turns out that gamma cusp is actually a well-defined IR quantity that shows up in other parts of physics as well. Good. So to be clear, when I talk about a form, I mean the integrand that gives you the log of the amplitude. This is unlike what people talk about in the usual loop amplituhedron, where that gives you the amplitude itself, right? Good. And because of dual conformal invariance, due to some symmetry of the integrand, you can write omega of L as just a function of this variable over here. Okay, where AB is one of the loop lines that you've introduced, and 1, 2, 3, and 4 are the twistors for the 4 points in your 4-point amplitude. Okay. Good. So I just want to point out that here, because this is a 1 over epsilon square divergence, if I do all the integrals except the last one, that is actually finite. So this is all to say that there are 2 IR finite quantities even after integration that you can get to. One is the integrand and one is the cusp anomalous dimension. So those are the quantities that we will be looking at, and they show up also, as I said, in other contexts of physics. In particular, they are this particular ratio of Wilson loop correlation functions. Yeah, so this is a null polygonal Wilson loop or square Wilson loop with 1 insertion divided by with no insertion. Okay, so as I said, this might have been a lot of physics words for some people in the audience, so let me summarize. There is some quantity that, when integrated, gives you the log of the amplitude, not the amplitude. And the idea is that that form is an interesting form. It has interesting properties. I'll talk about them in a second. And that's what we're trying to get at. And after we obtain that form, we would like to integrate it as much as possible until the last step, which would give you a divergence. So I hope that's clear then as to what exactly we are calculating. Okay. All right. Okay, so now this is stuff that people are more familiar with in the audience. So the context of this calculation will be the loop amplituhedron. So yeah, I feel like I don't actually have to repeat what people have said before me. But this is very much in the context of what Yara started talking about towards the end of his talk, right? Which is that the way that we want to think about this is that we have these Z1, Z2, Z3, Z4. So these are twistors, these are the external twistors for my 4-point amplitude. And for every loop that I'm considering, I want to add a twister line. So AB1, AB2, and AB3 means that this is a 3-loop configuration. Okay, and I want to think about all of these problems fully algebraically, which means I have this list of constraints. I'm at 4-point. So these are the only constraints that carve out my amplituhedron space at whatever number of loops. And what I need to do is say that, all right, the space I'm interested in is whatever is given by these inequalities, and I'm looking for the form on this space, right? And the canonical form on this space with the appropriate singularities on the boundary will be the form that I integrate to get the loop amplitude. Okay. Now, importantly, so let me just quickly read out what these conditions are. So this is saying that for every AB line, I mean AB1, 2, AB2, 3, AB3, 4, and AB4, 1 have to all be positive. The cross ones, so AB1, 3 and AB2, 4 have to be negative. And the hardest conditions to actually make sure it are satisfied are these ones over here, which I'll call mutual positivity. So that's just saying that for every 2 loop lines that exist, the mutual 4 bracket needs to be positive. Now, it's actually not that hard to just sit down and write down what this means algebraically. So if I said that, if I just parameterize my A and B twistors in terms of my external ones, which I can do in the following way with these parameters, then the first set of inequalities, these over here, just correspond to X, Y, W, and Z being positive. So as I said, those are very easy to make sure that you hit the right boundaries, because that's just this. The hard bit is making sure that you get these mutual conditions right. So if you look at what the mutual conditions become in this language, you get this quadratic inequality over here, which now you'd have to work simplex by simplex. So you'd have to assume something about the relative or the sign of x2 minus x1, w2 minus w1, pairwise, and you get different simplices. And then for every simplex, you can write down the form, and then you can sum over the forms. So that is somewhat tedious because very quickly it will increase in complexity. In particular, already at 3-loop, there is no nice form for this form. Yeah. So what we want to do is sort of bootstrap trying to find out what this form is just by using what cut conditions have to be satisfied. When I say cut condition, what I mean is that I'm sitting on one of these boundaries, or I'm sitting on a different boundary that shouldn't be a boundary but looks like a boundary. Okay. So the main trick that was introduced in this paper from 2021 was to think of this space or this form as the following graph. Okay, so this graph has 5 nodes. So each node is a loop. And it has it's fully connected with these blue lines. So every blue line is telling you that there is a mutual positivity condition between the different loops. Okay. Good. So I would say that this is the 4-point loop amplituhedron form, right? Because it's the canonical form on the space carved out by the correct conditions. All right. Now, you remember that what we want is actually the log of the amplitude. So it's not the form on the previous slide, but it's this more complicated form, right? Where all I've done is expanded out log of the amplitude. perturbativity. So the question is, I know that omega is a canonical form. The question is are these omega tildes forms on some nice space? Or what are they forms on? Or on what space are they a form? Okay. And that's what they showed, that yes, there is some nice structure to these forms. And it's actually very simple to see where it comes from. So these are two loop lines, and you say that they have a mutual positivity condition, right? So that's the form on that, plus the form on this, equals the form where there is no condition between these two lines, right? So once I use this graphical rule, I can rewrite every single one of these spaces as a sum over connected and disconnected graphs of this kind, where now my red links are negativity conditions, not positivity conditions. And again, if I have a sum over graphs in this way, I can rewrite that as the exponential of sums of connected graphs alone. Okay. This is just a graph theory. Good. So what that means is that the thing that I'm after is, I'll remind us all, is the log of this, right? It's the log of the amplitude. So to calculate the actual omega tilde, all I need to do is sum over all possible connected negative linked graphs. Okay. So if you ignore the x for now, this is the expansion that we want to do, right? We want to say that at the beginning, there's only one possible graph. Then there's this one at 2, 3. At 3 loop, there is this straight one, there's a branched one, there's a cycle, etc., etc. So clearly they get more and more complicated. But you can look at the following subset. You can look at the subset where it's just a straight line, right? So that's what I'm going to call the ladder contribution. And then you can look at the contribution where it's all of the trees, so nothing with a cycle in it. Yeah.
I'm sorry, is it obvious, maybe for this, why there are no contributions with disconnected? Because when you wrote that identity, red plus blue equals disconnected, but those are all gone now.
Yes. Yeah, so that's because of this. So this is exactly what one does with like amplitudes and Feynman diagrams.
Thank you. Yeah, of course.
Yeah. And again, it's mainly because it's the log of the amplitude. That's what let you get away with it. Yeah. Good. So this then gives you this perturbative in G expansion for the log of the amplitude. But as I said, there is no parameter that's controlling the number of cycles over here, but that's exactly the expansion we're going to do. We're going to do an expansion in the number of cycles in these geometries. I'll reiterate, this is an ad hoc expansion to do, and it's sort of it's because it works at the leading order that one wants to check whether or not it continues to work beyond the lead. Okay, so that's the pipeline. You want to start with your negative geometries, figure out what the form is, that'll tell you the integrand. You integrate, you resum all your integrals, and hopefully you get some of these nice quantities at strong coupling. Okay, so I keep saying that it worked at ladder, it worked at tree, leading order, etc., etc. So I just wanted to show you actual numbers. So ignore gamma for now. So F, if you sum all the ladders together, I'll remind you that the ladders were these straight lines, and these are the trees once you have branches. So the ladder gave you 0 at strong coupling. The tree gave you order 1. And then the actual answer, which is calculated using integrability, is order G. So clearly with the F, you failed completely. Well, okay, but you failed quite a bit because you didn't even get the correct order in G. With gamma cusp, on the other hand, you actually do come close. So all of these are order G and strong coupling. And these numbers actually come closer to 2. So 2 is the correct answer. 8 over pi is what you get when you resum the trees. And 4 times square root 2 is what you get when you resum the ladders. So this is kind of very suggestive that you're coming closer and closer to 2. And so this is why you want to check whether or not you are indeed coming closer to 2.
Sorry, when you
Yes.
resum I should add the tree and the ladder.
So when I say tree, I include all of the ladders and also just everything that looks like a tree, basically. So that's a strong coupling, and at weak coupling, also these numbers are, well, depending on who you ask, they're good or bad, but it's still kind of, I want to emphasize this is still a very small subset of graphs that you've summed, and you're still getting somewhat close. But admittedly not very close at all as compared to this, which is somewhat more miraculous. Okay. Good. So let's actually do this calculation now. So the integrand has 2 parts. It has a denominator and it has a numerator. The denominator is easy to predict because it has to have poles exactly at the boundaries of this space, and you know where the boundaries are, because that's given to you by what links exist or don't exist in your graph. The numerator is more complicated. So the numerator is some general function of these kinds of 4 brackets, but you know that it has to vanish on cuts that either take you out of the one loop amplituhedron or on cuts that require you to have a non-logarithmic singularity at some point. So double pole cuts are bad, and then cuts that take you outside the one loop amplituhedron are bad. And the other thing that is bad is if you do a cut and then you violate either the positivity or negativity of the link on the space that you've drawn for yourself. Okay, so the second cut only shows up when you do the one cycle. So let's first think about the first type. I forgot when I started.
You said it started at
3:15. Okay. Okay. Okay, good. So good. So there are these 2 types of cuts for the tree result. The first one I'll call a positive cut. Okay, so this is a cut. So when I say cut, I should emphasize. What I mean is that I choose a bunch of 4 brackets and I set them to 0. These are 4 brackets that appear in the denominator. So they're one of these 4 brackets, right? So when I sit, let's say, over here at this point where all of these brackets are now set to 0, I can write this in terms of my parametrization that I had earlier. And you can see that when I calculate ABCD, which is like loop line 1 with loop line 2, that gives me something negative. Okay. So if I was trying to write the form down on a space that had a positive link between these 2, this would be a cut on which the numerator had to vanish, right? Because it's an illegal cut. Similarly, I can also find a cut that is a negative cut. So if I had, let's say, these propagators set to 0, then ABCD would have to be positive, which means that if there was a negative link between AB and CD, this would have to be an illegal cut, and my numerator has to vanish on this. Yes.
So you're basically checking that hypersurface is cutting out the facets intersect outside or inside your geometry.
Yeah, that's another way to think about it. It's basically saying where are the zeros of your numerator, which is the same. Yeah, which is the same thing. Okay, so remember that depending on the type of link that you have to ask for either this to be a bad cut or this to be a bad cut. So now I can draw this sort of arbitrary graph with red and blue links. And I can now write down what the numerator has to be. And so this is what was presented. This is the solution that was presented in the paper from 2021 by Nima Yara and Johannes Henn. And this is the result that they have. And it's actually very, very compact result. And one thing you'll notice is that the way the numerator is built is actually link by link. And that makes sense because there is no other loop that participates in these conditions. It's just AB and CD. It's just two loops at a time that participate in these conditions, which means to satisfy them, you can just build the numerator link by link, which means all you need to do is think about what these two loops are doing or these two loops are doing, etc., etc. Pair by pair. Okay, good. So now we're in a position to think about what happens when I add a cycle in my graph. And when I add a cycle into my graph, I'm now allowed to do a different kind of cut that I couldn't do before. Or rather, there is now a new illegal cut that I have to make sure my numerator vanishes on. So this is the following. So if I ask for, so this is the line 1, 2, and these are 4 loop lines, AB1, AB2, AB3, AB4. And now let's say I set AB4, AB3 to 0. That would be, so actually, okay, first, I first ask for all of these loop lines to intersect 1, 2, right? So that is this condition over here. So ABI1, 2 is 0. Now I slowly move each of these lines into one another, meaning that I merge these intersection points sequentially together, right? So once I've finished that procedure, I've accidentally also set AB forward, AB1 to 0, right? So despite not actively setting that propagator to 0, I'll find that my form indeed has a singularity there. So that's what we're calling a double pole cut. And then that's the final configuration. So basically, you're not allowed to expose that double pole. Your numerator has to make sure that you can't see it in any way. So what that means is that, so this is the tree numerator, and this is a remainder. And this remainder now has to cancel out any contribution on a double pole cut that came from the tree. So one thing about this remainder function, which is interesting, is that, so consider these two different cycles. The only difference is this positive link versus negative link over here. It turns out that you can show that these remainders actually have to be the same, which means that you need to make sure that the remainder is compatible with positive and negative links. So that's actually a very, very strong condition. And it's strong enough that you can fully determine what the numerator is completely for one cycle. So this is L loop, one cycle. And this is the result. So again, it's not like pretty or anything, but it's very compact. Yeah, I just want to emphasize also that you can add as many branches as you want to this loop, and that's still an integram that we know what it is. So the fact that the one loop answer actually, a one cycle answer split up into a tree plus a one cycle contribution actually continues beyond that. So say I had a 2 cycle, 3 cycle, etc. I can break it down in the following way, where it's the tree bit, a loop times tree, loop times tree, loop times tree, and then a true 2 loop contribution. So you can do this decomposition, and it allows you to basically write down all of the four point integrands just by doing this like bootstrappy, does it vanish on the correct cuts kind of requirement. Okay, so in the last part, I want to talk about this pipeline and how far along it we are. So at this point, we're here. And in case you can't tell by the number of slides left, I'm not actually going to make it all the way here, but we will do a few integrals. And I want to show you some of our integrated results. And I'm happy to talk to you more offline about how we plan to resum these or how we're planning to get our strong coupling results, which hopefully will be done soon. But all right, so let's start integrating. Okay, so this is the most generic integrand that we have right now in closed form. We have a few of these as well, but it's not as much use if you can't actually integrate them. And so unfortunately, the only integral that is available for a cycle is the triangle. Okay, so it's the 3-loop 1 cycle that is available, but you sort of you can use the fact that this triangle integral is known to then add branches, etc. So how does one do that? You use the following very simple differential equation. Okay, so that allows you to basically move my unintegrated loop inwards. Okay, so if I want to, so this was calculated by physicists maybe in the 2010s, I think. And so you can basically invert this differential equation to calculate what this is, because you know some boundary conditions that this integral has to satisfy. In addition, because this is an unintegrated loop, once it sits in the middle of your picture, this side of your picture has nothing to do with the other side, right? So it fully factorizes on either side of your unintegrated loop. This means that despite the fact that the only integral we knew how to do when it came to 1 cycle graphs was this one, we can actually we can use our differential equation methods to calculate all integrals of this type. Okay, so it's a triangle with a branch attached, and this unintegrated loop can be anywhere. Okay. To give you an example of what these integrals look like, yeah, so this is the simplest possible one that we calculated, and it's just a bunch of harmonic polylogarithms, which are just generalized polylogarithms, except their arguments are 1 minus 1 of 0. Yeah, so it's this, and it has some constants as well. It has uniform transcendentality. Yeah, and it has some nice structure as you keep. It has a predictable structure as you add more and more legs to this triangle. Now you remember that this was actually still F because it has Z dependence. We want to get eventually to gamma cusp, and the way to do that is to perform yet another integral, some contour integral over Z. So the details aren't important. What I wanted to show was this table over here. So this table shows you that, so the first line of this table gives you the comparison between the tree gamma cusp and the true gamma cusp. At first order, there's only one contribution, so tree equals true. Similarly, second, there's only one graph you can draw with 2 nodes that is connected. Now, when there's 3 nodes, you know that again, there's only 3 things you can do. 2 things you can do. You can either draw 1 tree or 1 cycle. And since we know 1 cycle, these contributions add up to 1, as they should. Okay. Beyond that, there are contributions that we are missing since we don't know the full 1 cycle, 2 cycle results. But one can still calculate what I think of as the triangle and friends result, and get these numbers over here. And you'll notice that they all bring you closer to the correct answer. But what I think is interesting is that they all bring you closer by very small numbers. Right? So this really does look like you're doing something perturbative, because this contribution, the second row, is so much smaller than the first row. Right? So it's bringing you closer, but by very, very little. And I think it's one of those questions then that you should ask yourself why certain graphs seem to contribute so much more versus so much less than others. Okay, I will quickly point out though that the the actual strong coupling results that people got in the past, they didn't actually do the resummation. What they did was solve a differential equation. And you can set up a differential equation like this for the triangle as well. Sorry. So you can set up a similar differential equation for the triangle where now instead of this being a homogeneous Laplace equation, you're going to have some very complicated source term on the right-hand side, which is a combination of harmonic polynomials. So if that's something people like doing, solving a Laplace equation with a complicated source, please come talk to me after this. Of course, you can find solutions for such things, and you should talk to Umar, who knows more about this. But the form of those solutions aren't very illustrative so far. So another way to do this is to just do it. So you take the contour integral of your triangle times your ladder, and you do this integral. Now it's not, again, non-trivial to get this in closed form, and that's something that we are actively working on now, and I'm hoping it'll come out soon. Okay, so I think I'm okay on time. Yeah, might have gone a bit too quickly for some people, but here are the questions that I think one needs to think about. The first is why this seems to be an expansion at all, given that there is no parameter that you're expanding in. There are, of course, more technical questions, such as, can you do that integral that I showed you in the previous slide? But I think whether or not this is actually an expansion is a more interesting, sort of deeper question. There are, of course, other technical problems, such as whether you can do all of these integrals. So as I said, the problem of actually writing these integrands down is sort of solved, at least I'm considering it solved. But to actually do the integrals is another question. I think also more generally, the question of which Feynman graphs give you the majority of your answer is a question that maybe we should be asking when it comes to actually getting to the end and getting an answer or a number out, which is ultimately the goal if you want to do like calculator scattering. Yeah, so that's kind of all I wanted to say. Thanks for your attention.